Welcome, everybody. This is our first 10 minutes with Harry presentation. One of the issues that I have with ECG reporting is that I occasionally get back a report saying, is this a right bundle branch block? What do I mean by this? Well, this is one of the ECGs that was returned to me because it was reported as normal. And indeed, it is correct. It is normal. However, the 17-year-old patient was told by me, by the technician, that this is an incomplete or partial right bundle branch block. So I looked again at the tracing and I saw that there was an SR-, which suggests, of course, that this has a bundle branch block. However, the QRS is only 76 milliseconds. So clearly it is not a bundle branch block, and clearly it's normal. Let us review then the right bundle branch block. For a right bundle branch block, normal QRS width is less than 100 milliseconds. For incomplete bundle branch block, it's 100 to 119 milliseconds. And for a bundle branch block, it's greater than 120 milliseconds. We, of course, all know that. For right bundle branch block, the RSR prime is in leads V1 and V2. And in leads 1 and V6, the R wave is of greater duration than the S wave is of greater duration than the R wave, or the S wave is greater than 40 milliseconds. So let us now return to these ECGs and show you another one, which is a normal ECG with an RSR prime again. And you can see that leads 1 and V6 do not have S waves that are wide in them at all. The QRS is 90 milliseconds. But this is often also still called incomplete right bundle branch block. Here is a third one, and you can see that in V1, it really does look like incomplete right bundle branch block, but the QRS is only 96 milliseconds. So in order to get to the incomplete level, one needs to have a QRS of 100 milliseconds. But I stress to you that even though this is the case, it is still completely normal ECG. And although it fits the incomplete right bundle branch block criteria, I believe it should be called a normal, or if you're going to call it incomplete right bundle branch block, then you should state after that a normal ECG. Take, for instance, this ECG tracing with an RSR prime, and it looks like an incomplete right bundle branch block. Indeed, the automatic report from the ECG machine says incomplete right bundle branch block, otherwise normal ECG. I agree with that. But when one looked at the QRS width, it's only 92 milliseconds. So here is in fact an error in the way the ECG is interpreted by the ECG machine. Let's go a bit wider now, and we can see that QRS is 112 milliseconds and has this RSR prime, but otherwise completely normal. If it's normal, call it normal. Here is then where it just gets to 122 milliseconds with an RSR prime in V1 and V2. And you can start to see now that in leads 1 and in V6, the S wave is widening. And so we can, in fact, call this a right bundle branch block. But as you can guess, this is really a normal ECG. Note, however, there's also a left anterior hemiblock or fascicular block as well with the left axis deviation. Let's go a bit wider still again, and now we're at 136 milliseconds, and we're clearly into the right bundle branch block range. So when we want to summarize this, normal, you can see, is less than 100 milliseconds, and we've got the first two, 76 and 100 milliseconds, and you can see there are quite dramatic RSR in the borderline one. Then we have incomplete and then right bundle branch block. So you can see how it's developing, but you can look at all these ECGs and agree that they are virtually similar to each other, and all of them are really within normal limits and should be regarded as such, even though the last one has been referred to as a right bundle branch block. I just want to talk a little now about right ventricular hypertrophy. The literature is extremely vague in this regard. Most people avoid even discussing it. And the way I have done it for the last 40 years is to look at V1, V2, V3, and if there is a negative T wave with the right bundle branch block in these leads, then I regard this as right ventricular hypertrophy. I am not sure that there is enough scientific evidence to prove that I'm right, but nevertheless, it is a good working hypothesis. Here is the ones, two other ones with a right bundle branch block to the left and to the right with yellow highlight, and you can see the T waves are normal. And that is the case with right bundle branch block. In order to have just a complete right bundle branch block, one needs to have T waves upright in 2 and V3. But if they're negative, then we think of right ventricular hypertrophy. Here is another one where the T wave inversion is extended, V4, V5, and there are tall R waves in V5 and V4, and this suggests that there is left ventricular hypertrophy as well. So we have evidence or suggestion of right ventricular hypertrophy, and then we also have left ventricular hypertrophy. So we can call this biventricular hypertrophy. Again, it's not a absolute diagnostic criteria, but rather it's a suggestion, and it is worthy putting it in the report. You all know about left anterior hemiblock with a left axis deviation in leads 1, 2, and 3. And then we also can have a left posterior hemiblock, and this is a right axis deviation, a deep S wave in 1, positive in 2 and 3, which in the presence of a right bundle branch block really suggests that this is a bifascicular block and that this is right bundle branch block and left posterior hemiblock. Just like to finish off by showing you that right bundle branch block may not always be present in the ECG, but rather it can be present each alternate beat, and this is an alternating right bundle branch block, and the electrophysiologists can explain these by changes in the right bundle branch with alternate beats, and it becomes refractory, an alternating right bundle branch block. Thank you very much.